Okay, so this video is section 1.1 and 1.2 part 2. So now we're going to just look at some of the common functions that you guys should be familiar with at this point. And I'm going to point out a few points that it would be helpful to know just really fast. And they're all points about the origin. Now that's not the case for these first two common functions, which are actually both linear functions. Oh, my numbering's off here. So that should be 1, 2. Oh, you know what? I think I meant to put them all as 1 because they are all actually linear functions, right? So these three equations actually represent the equations of lines and lines that are functions. Notice that the equation of a vertical line is not here, but that's because, remember, a vertical line is not a function. It would not pass the vertical line test. So the first equation that I have here, f of x equals to ax plus b, this is really slope-intercept form of the equation of a line, right? We usually would use m here instead of a, where m is the slope, and then b is our y-intercept, or helps us identify what the y-intercept is, because the y-intercept would be 0, b. So obviously this is a general equation of a line that is in slope-intercept form. The example of the line that I drew here would have a y-intercept of 0, 4, so b would be equal to 4, and then it has a slope of positive 1/2, because we have to go, so if we pick one of the points on this line, like if I pick the point 0, 4, to get to the next point that I have graphed, I would go up 1 unit and then to the right 2 units. So rise over run, that would be 1/2 of this would be the slope. So the equation of this particular line would be y equals to positive 1/2 x plus 4. And then the constant function, f of x equals to c, where c is a constant, so just a real number. The example graph that I have here would be f of x equals to 6, or y equals to 6. It's a horizontal line. Each point on the graph that I have drawn has a y-coordinate equal to 6, so y is constant. Also a line. And then the identity function. You could think of f of x equals to x as being in slope-intercept form. It's just that the y-intercept is the origin, is 0, 0, and the slope is 1. So every point that lies on the identity function will have the same x and y coordinate, right? We have plotted 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, and so on. But you could also think about other values on there, right? Like 1/2, 1/2, even pi, pi. But this is also known as the identity function, but it is a linear function. It's a type of linear function. All right, the square function, also known as quadratic function. This is f of x equals to x squared, is like the most basic quadratic function. And the points that I have plotted on here, I apologize, my curve is a little funky, but I have the point that's at the origin, and then we have 1, 1, negative 1, 1, 2, 4, negative 2, 4, and those are the points that in section 1.3, when we are talking about graphing functions using translations and transformations, and we treat for a quadratic f of x equals to x squared as the parent function, those are the points that I think about when I think about transforming and translating. Okay, the cube function. I had a student years ago refer to the cube function as the chair function. Just it helped him remember when he was looking at it, he saw a chair. So I always refer to it now as the chair function as well. But the points that I always think about are especially -1, the origin 0, 0, and 1, 1. And then it can also be helpful to know 2, 8, and -2, -8. Okay, so that's the cube function, or cubic function. The square root function. Helpful points, or points that I like to just use for translations and transformations, would be the origin 0, 0, then 1, 1, 4, 2, 9, 3. Right, then next I would probably use 16, 4, but especially the first 3 points, 0, 0, 1, 1, 4, 2, for when we want to graph using translations and transformations. The cube root function, that same student that referred to x cubed as being the chair function, referred to cube root of the cube root function as the sideways chair. So I refer to this as the sideways chair. So -1, -1, 0, 0, and 1, 1 are the points they use when then thinking about translations and transformations, which we will discuss in section 1.3. And then also 8, 2, and -8, -2. The sideways chair, you can kind of see it if you think about like a lounge chair. Okay, the absolute value function, 0, 0, and then 1, 1, 2, 2, 3, 3, 4, 4, and so on, and then -1, 1, -2, 2, -3, 3, and so it ends up making a V. I think at the end here I'll talk about, actually maybe I'll save that for section 1.3 when we take the absolute value of functions, what it ends up doing to the graph. I'll talk about that in 1.3. All right, and then the last one I have on here is the reciprocal function, also known as a rational function, or just like the most basic rational function. And in chapter 2, we will study rational functions, more complicated rational functions, way more in depth. Let's look at 1 over x, though. Okay, so the points that I have plotted on here are 1, 1, -1, -1, and then 1/2, 2, 2, 1/2, -2, -1/2, and -1/2, -2. Now, as x, let's focus on as x is approaching 0. So if we think about x, let's say from the left-hand side. So as we choose values of x that get closer and closer and closer to 0 from the left-hand side, let's think about what ends up happening to the y values, the y coordinates. So if we substituted -1/8 into our function, our output would end up being -8. -8. If we substituted -1/100th, then our output, our y coordinate, would end up being -100, and so on. And -1/1000th, our output would end up being -1000. So the values get smaller and smaller and smaller and end up approaching actually -infinity, which is what our graph what that arrow down here indicates. So we can say as x, I'm going to use the arrow. Okay, so as x approaches 0, and the notation, and we'll talk about this again in chapter 2. But as x approaches 0 from the left, and to indicate from the left, I'm going to put a negative symbol where like an exponent would be. So as x approaches 0 from the left, f of x approaches negative infinity. As x approaches 0 from the right, and the notation is I'm going to put a plus sign where the exponent would be. It looks like the function approaches positive infinity, right? Because as x gets closer and closer to 0 from the right-hand side, like if we plug in 1/8, our output would be 8. If we plug in 1/1000, then with 1,000 would be our y-coordinate. 1/1,000,000th, right? Then our y-coordinate would be 1,000,000. So the y-coordinates just end up getting larger and larger and larger. However, if we were to plug in 0, 1/0 is undefined. So we actually have what we call a vertical asymptote that occurs at x equals to 0. And I write VA at x equals to 0. That's my notation for the vertical asymptote. And we will discuss this more, but when you have a vertical asymptote, the function as it approaches that vertical asymptote will either increase or decrease without bound, meaning that the function will either end up approaching positive or negative infinity. Now notice we also have some interesting behavior as x gets really large as well as x gets really small. So that was as x approaches 0, but now let's look at as x approaches negative infinity. So if we were to plug in larger and larger values, so like -100, -1,000, -10,000, -1,000,000, our y-coordinates would end up getting smaller and smaller and smaller, getting closer and closer to 0, but they would never actually, the y-coordinate would never actually be equal to 0. So what we can say is as x approaches negative infinity, it looks like the function is approaching 0. However, it's not actually going to end up being equal to 0. It's just going to get really, really close to 0. And then as x approaches positive infinity, something similar is going to happen. So if we're plugging 100, 1,000, 10,000, 1,000,000, 1,000,000,000, and for x, 1/1,000,000,000 is a really, really tiny number. But even though the values for y get smaller and smaller and smaller, they will never be equal to 0. So we can again say that f of x would be approaching 0. This ends up meaning that there is what we call a horizontal asymptote at y equals to 0. So for now, it's going to be important that you know that the horizontal and vertical asymptote exist for this particular function, for f of x equals to 1/x, because this is going to be one of the important functions, a parent function that we use in section 1.3 to graph by translations and transformations. It's kind of an intro into our study of rational functions, which will take place in chapter 2. But for now, you just need to know that the function 1/x has a vertical asymptote. Here, I'll even highlight that. Has a vertical asymptote at x equals to 0 and a horizontal asymptote at y equals to 0. Part of this class is learning as many characteristics or ways to identify characteristics about functions as possible. And you're going to continue to do more of that in calculus, and you'll learn to identify different characteristics, like also from like a calculus perspective. But the idea is once you have all this knowledge about how to identify important characteristics about functions, equations of functions, and graphs of functions, then whenever a function is used to model a certain situation or data, you can then identify important characteristics that can help you with analyzing that data or that information that it models. And one of those pieces of information are whether or not a function is even or odd, and what that tells you about the function. So, to determine whether a function is even or odd, or neither, a function can be neither even or odd. To determine if a function is even or odd, you're going to replace x, or you're going to evaluate the function at negative x. What that does is it's almost like forcing a horizontal reflection of the graph, because you're taking the opposite of all the values in the domain. So when you replace x with negative x, you're forcing a horizontal reflection, and then you want to simplify the equation to see what it simplifies to. If the function simplifies to the original function, that means that a horizontal reflection does nothing to the graph. So a reflection over the y-axis does nothing to the graph of the original function. And therefore, we could say that the function would be, its graph would be symmetric with respect to the y-axis or the vertical axis. Okay, so what this says is that a horizontal reflection looks the same as the original function. If, when you replace x with negative x, so when you apply that horizontal reflection, you simplify the equation and it ends up being equal to the original function times -1, so negative f of x, that would mean that a horizontal reflection ends up looking the same as a vertical reflection. A horizontal reflection looks the same as a vertical reflection. So if you take the opposite of every value in the domain, it ends up giving you the opposite y-coordinate from the original function. So we refer to that as being symmetric about the origin. And I always had a hard time with visualizing what that means for a graph to be symmetric about the origin. And what it means is that a horizontal reflection would look the same as a vertical reflection. Or if you thought about applying a horizontal and a vertical reflection, then you would end up with the original function graph. Okay, so in other words, a function is odd if a horizontal reflection looks the same as a vertical reflection. So let's actually determine, and a function can be neither even or odd, meaning a function cannot have symmetry about the y-axis and not have symmetry about the origin. That happens. Let me choose another color. Let's use blue again. Okay, so if we want to determine whether or not f of x equals to absolute value of x minus 8 is even or odd, we're going to evaluate f at negative x. And since the absolute value bars there are going to make whatever is inside the absolute value bars positive, absolute value of negative x would have the same value as absolute value of x. Therefore, we could say that this equation simplifies. The outputs would be the same as just the function f of x. And therefore, f of x is an even function, meaning its graph would be symmetric about the y-axis. And if you were to graph that function, you would see that. If you applied a horizontal reflection, it would look the same as the original graph. Okay, so let's see about the next function. So we're going to evaluate the function g at negative x. Okay, so if we simplify that, we would have negative 1 over x plus 2x. Notice that each term here has the opposite sign in front of it as our original function. So if we were to factor a negative out, we could say that this is equal, g of negative x is equal to negative g of x. And therefore, g of x would be an odd function, which means that the graph of g is symmetric about the origin. And h of x, so let's evaluate h at negative x. We get the square root of 2 plus x, which there's no way that that simplifies to be negative h of x or h of x. So h of x is actually neither. It's not even and it's not odd. It means the graph of the square root of 2 minus x is not symmetric about the origin or the y-axis, which would make sense if you graphed it. Okay, so we're going to also look at graphing piecewise defined functions. We can create functions that behave as different functions based on the input value. I have an example of a piecewise function here, the equation of a piecewise function right here. It's super important to remember that a piecewise defined function is one function that has one domain and one range. Even though the function is made up of pieces of other functions, it's still one function. I've seen different approaches to teaching graphing piecewise defined functions. I think it's best to just go one piece at a time, to use the endpoints of the intervals to help you find points for where the graphs will end up switching. So, for example, this function f of x equals to x squared when x is strictly less than 2, and 4 when x is greater than or equal to 2. So that means from negative infinity up until 2, but not at 2, the graph is going to look like x squared. So like if I wanted to plug 2 into that first piece, I would have the point 2, 4, but the graph is not actually defined there. At least not just looking at that first piece, because it's for x strictly less than 2. So then you can think about plugging in values like f of 1 would be equal to 1, f of 0 would be 0, f of negative 1 would be 1, and just end up plugging values into that first piece. So values that are on that interval, I'm plugging into that first piece. And then if I were to evaluate f at x equals to 2, 2 lies on that second interval. So actually, I am able to fill in that point at 2, 4. And then every value to the right of 2, so from 2 to positive infinity, the output would be 4. So to the right of 2 would actually look like a horizontal line. Okay, so let's go ahead and state the domain range and then also the intervals where the function is increasing, decreasing, or constant. So first for domain. Reading that graph from left to right, I can see the domain would be all real numbers, so from negative infinity to positive infinity. The range, reading the graph from bottom to top. Okay, we're talking about the intervals of y values. The interval of y values where this function is defined, it looks like it would be from 0 to infinity. Now for increasing, decreasing, or constant, our textbook's definition for increasing, decreasing, or constant is if on an open interval, as x is getting larger, let's say if on an open interval as x is getting larger, the y values are also getting larger, then the function would be increasing on that open interval. And you could imagine if you were walking along the graph, because when we're talking increasing, decreasing, or constant, like domain, we're talking about intervals of x values. So that means we read the graph from left to right. So if you were to imagine yourself walking along the graph, going from left to right, if you felt like you were walking uphill along the graph, then the graph would be increasing on that open interval. So as x increases, y increases. Now, if as x is getting larger on an open interval, y is getting smaller, then we would say that the function is decreasing on that open interval. And if you were to imagine yourself walking along the graph, you would feel like you're walking downhill on that interval. And then if as x is getting larger, y is staying the same or staying constant, that means that the function is constant. And if you were walking along the graph from left to right, you would feel like you're walking on a flat road. We are only using open intervals for now. In calculus, you will have a new method of determining where a function is increasing, decreasing, or constant. And you will be able to decide whether to include endpoints or not. But for now, for increasing, decreasing, and constant, we will use all open intervals. So reading, and we're only reading the graphs. So for this particular function, it looks like between 0 and 2, the graph is increasing. I would feel like I was walking uphill if I was walking between 0 and 2. For decreasing, it looks like from negative infinity up to 0. I would feel like I was walking downhill. And then from 2 to infinity, the function's constant, and I would feel like I was walking on a flat road. Now, there doesn't have to be an interval for each. Like a function can be increasing everywhere, or decreasing everywhere, or constant everywhere. That's a special type of function referred to as a monotonic function. Or it could just be increasing and decreasing, or there could be multiple intervals that we would list where the function is increasing or where it's decreasing. Let's look at this next example. Let's graph first. So from negative infinity up to -1, the graph will look like x squared. So I can actually fill in that point at -1, 1. Between -1 and 1, the graph will look like x cubed. Oops, not a filled in point. Notice the endpoints on that middle piece are not included. And then for x greater than or equal to 1, the graph will look like g of x equals to x. So I can fill in the point 1, 1. Okay, domain. Reading the graph from left to right, looks like the domain would be all real numbers. The range, reading the graph from bottom to top, would be -1, but I'm not including -1 because notice there's an open circle there. So -1 to infinity. For increasing, looks like from -1, remember increasing, decreasing, constant, we're using only open intervals, would be from -1 to infinity. Decreasing would be from -infinity to -1. And it doesn't look like this function is constant anywhere, so I'll use empty set. Okay. Now, if there were multiple intervals, multiple open intervals where the graph was increasing or decreasing or constant, I would just separate those intervals with a comma. And we can discuss more in class why that is, instead of using a union. Okay, and then the last thing we're going to talk about is continuity. So where a function is continuous versus discontinuous. This will be discussed more in calculus, and you will have a more formal method of determining where a function is continuous or discontinuous. But our definition is, for now, will be that a function is continuous if you can trace the entire graph without picking up your pencil, which implies that there's no holes or jumps in the graph. So this first piecewise would be continuous. I could trace the entire graph without ever having to lift up my pencil. This graph, however, would not. The second piecewise would not, because I would have to, at x equals to -1, I would need to lift my pencil. So a function is discontinuous if there is a hole or jump, meaning you can't trace the entire graph without picking up your pencil. Okay, so that is the end of section